Hi guys, welcome to the afternoon. Today is Thursday, we're not in February, March 4th actually. And as promised, we're going to be doing more problems from this chapter 22, okay? And let me check exactly the lecture where we stayed last time, because we're not going to do all of the entire basically period for problems. Because we only have really two problems, but I want to do them thorough because we want to understand them both, okay? I know we already did two problems, problem 52 and problem 53, and I hope that they held to all of their promises in terms of the techniques they use, both problems. One of them used calculus stuff and how to use the symmetries and things like that, and the other one basically mathematical trick to solve problems that seem to be impossible to do. I mean, not impossible, I mean, extremely hard to do by hand manually, okay? So that is basically these two problems. So we still have two more problems. So let me look at the notes from the lecture to make sure that we're in good shape. And there is only one thing that we're supposed to do and we didn't do in the lecture. So I think that we need to borrow this time first for it. And as promised, I will go thoroughly on problem 43 and to some extent, at least with problem 55 using Excel. And basically close this one, okay? So let me share with you the screen. I want to share the OneNote first. What happened to my, oh, I did not share anything, share. Okay, good. So from the lecture, basically, here is a question that I know that we have this curly things, and I'm hoping that you guys will get yourselves accustomed to. There is actually something else that I'm thinking to do, which I did in the past, and I found it actually kind of useful too. So I might assign another assignment related to this stuff in here, okay, independently. But here is a question, okay? We wanted to know if the electrostatic force, which is this one, F equals to QE, derives from a potential. For that, we argued that if I can find the electric field itself derives from a potential, in other words, if I can find a function V scalar actually, function V that depends probably on X and Y and Z, but it's still a scalar. It's not like a vector that you have to worry about its X component, Y component, and Z component in space, or its radial component and both angular components, which are three still components in polar coordinates. Whichever symmetry you have, you will have three components of a vector. Instead, we find just a function that depends, of course, on those variables. There is no question about it, but it's only one function instead of three, okay? If we can find that so that E, the electric field, is written in the same form as minus the grad of this function V, then I can say, since F is equal to QE, in the same token, the work, or the energy in this case, is going to be QV. In other words, this F is going to be actually equal to minus Q delta V, okay? So that is basically what this is. So if I work out my way around it, since F is minus grad of that U, then U in this case must simply be equal to QV, okay? So in other words, this potential, which is actually I'm going to call the electric potential, and this is the potential energy, are related to one another via the parameter Q, via the charge, that's all. Just as much as the force and the electric field are related to Q. So this is in Newton, by the way, and this was in Newton per Coulomb. And the Q in here is that factor. So if I have an electric field somewhere, I have, so if I go in here in space and I have a vector field in here, E, then I have a force, and that force in magnitude is equal to QE. That's a vector. This says, on the other hand, if I have a potential in this point, it's not a vector, it's just a number, like 12 volts or 17 volts and things like that. I actually have energy in this case, and this energy is this many joules, okay? Just as like that. So it's not a vector, it's the same point in space. As a matter of fact, this point is P, and this is the same point in P in space. So the units for V is actually the volt, okay? So this is the challenge that we are trying to resolve, okay? So that is the idea that we're trying to get to. So instead of actually dealing with energy in joules, we're going to be dealing with voltage in volt, okay? And once we have volt, if you want it in energy, all you have to do is multiply it by the charge and you have the energy. Same thing. When we were dealing with chapter 22 and 21 with the electric field, all we have to do is actually multiply that by Q, and now we have the force in Newton. The advantage of doing it this way is actually this relationship. If, and this is a big if, okay, I didn't say we have done that. If this is true, if the electric field derives of a potential, and if we have a potential really, then all I'm going to do is take its derivative with respect to x in the x direction, with its derivative with respect to with respect to y in the y direction, its derivative with respect to z in the z direction, because this is a multivariable function, and now I have the electric field. So the task of finding a vector, which is complicated usually because of it has 3 components, becomes just the task of having just a single function. Once we find it, we have found the electric field. We're back in business. So this is the whole promise. So I'm going to do a point charge, which is the easiest of them all. So a point charge, the electric field that a point charge is, if you guys remember, was Q over 4 pi epsilon naught times 1 over the distance squared times r hat. Okay. So for me, this electric field, this is a point charge, by the way, point charge. The electric field is radial. And I know the vector r is this way. So this is the vector position. One way to change the vector position is changing its length only by adding a dr to it in the radial direction. Another way of changing the the vector position is by changing its direction by an amount d theta. This stuff, by the way, you should have seen it in physics 4a, d theta. The arc distance is r d theta, actually. This is in the theta hat direction, okay? So in general, if I want to find the displacement, remember, we said that the potential in this case, which is equivalent to the potential energy, must be then the integral of EDR, this dot product. E is radial. The dr could be radial or has an angle in it. It doesn't matter, since it's the dot product of r hat times dr r hat plus something that involves theta hat, this product is going to be 0 because they're perpendicular. Cosine of 90 degrees is 0 because this is the dot product of this vector and it's perpendicular. So the only thing that is going to stay is the r hat times r hat, and that is a unit vector. When you multiply a unit vector by itself, you're going to get 1 because its length is 1 and the length of the second one is 1 and the cosine of the angle between them is 0. The cosine of 0 is 1. So at the end, this potential then boils down to finding this integral Q over 4 pi epsilon naught, and I'm left with dr, that is from the radial displacement, dr, over r times r hat, and that is 1, because the other one is going to be 0 anyway, okay? So this is the integral r squared, I'm sorry. That is this square in here. This is the integral I'm supposed to find. What is the integral of 1 over r squared? What is the integral over 1 over x squared if you're going to do this integral? Isn't this, and help me out, okay? Negative 1 over x plus constant? Yes or no?
Yeah, that looks right.
Yeah, because if you take the derivative, you're gonna it's already to the power -1. Okay, so you're gonna derivative minus another 1, which is going to be -2. So this is the derivative, and then the minus in here will cancel the other minus. So therefore, the answer to this one, of course, I have a minus already, so it's going to be a positive Q over 4 pi epsilon naught times 1 over R. So this is the potential. If you are curious trying to write it in terms of, don't forget that R, the vector position in Cartesian coordinates, is written as x squared plus y squared plus z squared. This is something that you probably have seen. You should have seen at least in 2D, that the vector R is in 2D has an x component and a y component, that is x and y. So using the Pythagorean theorem, R squared is equal to x squared plus y squared. Obviously in space, you have to add a z squared to it, that's all, okay? So if you're curious, what happened to the x and y and z, they're here, they're inside this square root, okay? So this is the potential for a point charge. Now, if I have a bunch of point charges, I have 2 of them, who should we call? What do you think we should do? Our BFF. And that is, if I have this charge and this charge, and I know this potential, this charge creates a potential which I just found it to be Q over 4 pi epsilon naught in this space divided by the distance only. So there is a point charge. This is the potential in here, plus a constant, of course. That integration really has to have a constant in it. So I cannot really define it as such, because this is an antiderivative. This is an indefinite integral. So the point being in here is this is the potential in this point, plus that constant in here. Now, if I have another charge in here, so this is Q1, so I have to put Q1 in here. If I have Q2 now, I can find the potential energy due to this charge while this one doesn't exist, and it's going to be another number, which is going to be Q2 over 4 pi epsilon naught times 1 over this distance. So now this distance is R1, this distance is probably R2, and that's it, plus another constant if you wish, okay? And constant plus constant is going to be another constant. So we're going to use the superposition principle. Superposition principle. And say that no matter what distribution of charge, we really have a potential. And it's the sum of all of this stuff, okay? So there is a potential, and we can calculate it. So if you have 2 charges, we can do it. So now we're in business. That means the potential exists for a point charge. That means the electric field is actually a conservative field. And that means the electrostatic force is a conservative force, just like that of a spring, just like of that of the gravity. And it's an energy of position. Indeed, it is, because it depends like 1 over distance. So it depends just on the distance. And it doesn't depend on the path that you take to go from point to point. So this is the point that I wanted to finish at least for the lecture, because we finished on a bad note. We finished on math stuff, and I really don't like that. So we wanted to talk still physics. And this is really the idea behind it. So the potential exists. And if you're curious trying to find it for 1 point charge is just Q over 4 pi epsilon naught times 1 over distance, end of the story. So for a point charge, it's 1 over 4 pi epsilon naught times Q over R, plus, of course, constant. It's always there, a constant. When you're dealing with potential, there is always a constant. It's only defined within a constant, that's all. Because most of the time what matters is the difference in potential. It's not the potential itself that matters. For example, the plug in your household, it says 120 volts. What they mean by it, there are 2 ends in it. The difference between both of them is 120 volts. That means one of them could be 1,312. The other one is add to it 120 volts, or subtract from it 120 volts. As a matter of fact, it's alternating current, and we will see that. Sometimes it's more than or less than, and on the average, it's going to be 120 volts. So that's basically how the current is. That's how the voltage is. And this is the same thing is true in here in this case too, because always, even the gravitational potential energy was defined within a constant. Even the spring constant, if you really think about it, for the spring, it was the integral of -1 multiplied by the negative, so it's going to be the integral of kx. So when you integrate that expression, it always has a constant. But what matters in this case is how long did the spring compress or elongate. So what matters is just the difference in potential energy there. And what matters for the case of gravity is only the difference in potential energy. And what matters in this case is only the difference in potential energy. And for the case of the electric field, the difference in electrical potential. Okay. So when we meet on Tuesday, as far as the lecture, we're going to be picking it up from here and elaborating on this idea of electric field and how useful it is for us to calculate electrical potential, and how useful it is for us to calculate electric fields. Okay? We do problems now? Yes or no? I need your feedback, guys. You guys quiet. Shyness is one of the bad things to have in physics. You cannot be shy. You have to really speak up. We do problems?
Yes.
Okay, thank you very much. Okay. Somebody.
Yeah,
Otherwise,
I'll be the one. Yeah, I'll be the one.
Okay. No, I want everybody. This is not a democracy. Everybody has to vote and has to speak up in here, okay? This is a dictatorship, okay? Everybody will vote and vote yes at the end. No, okay? So everybody really has to participate in this one, okay? We don't want to... Okay, so the problems I promised to do now, after we did 52 and 53, are problems 43 and problems 55, okay? I thought we promised another problem or something like that, but anyway, it's fine. So, problem 43. Problem 43 from this edition, I think it's problem 50, it's problem 45 from the 14th edition. So if you happen to have the 14th edition before you, it's on page 748 on page on 14th edition, and it's 744 on this edition, okay? So that you guys are following and making sure that everything is clear. Problem 43. So what the problem says is, a small conducting spherical shell. The key word to take from this one is conducting. This is a big word in here that they use. We've been dealing with insulating, and that has implications in terms of charge distribution. So does this word, okay? Now we are dealing with another beast. We are dealing with another animal when it comes to materials, okay? So this is not the insulating where we had like the problem 52 or even problem 53, which they start, both of them. I mean, the first one starts with an the problem 53 starts with an insulating, and the other one, but the spherical symmetry distribution. So there is, the other one implies that's an insulating because it tells you that the distribution was uniform. Okay, it has to be an insulating because if it's not, it cannot be uniform. You know, charges cannot exist, do not. So this is the key thing in here. Do not exist inside the bulk of a conductor. So in other words, you cannot have uniform charge distribution. If you happen to sprinkle 10 coulombs on a conductor, it's not going to go uniform. It's going to go only to the surface. It's not going to go inside the material. Okay, so that's what that means. Furthermore, so this is one thing that I'm going to conclude from this word. The electric field also is equal to 0 inside the conductor. So that's what this, so when you're reading a problem and you're trying to solve it, you need to decipher what those words mean. You need to decode them to help you work the problems, okay? Because they have a meaning, and that meaning can be extremely helpful to solving your problem. Okay, so it's an inner shell with inner radius A. So I'm going to draw a shell in here. It has to be small enough for me because apparently we have another one. So this radius is A, and this radius is B, and this is a conducting sphere. So whether they ask us or not, I know the electric field is equal to 0 here inside. Okay? So that is a fact because of the fact that this is a conductor. Okay? We know that. Now that is the inner shell. Is concentric, meaning it has the same center. So this is the center with another one, another shell, with the inner radius C and outer radius conducting also. The other one also is conducting. So I have to draw a sphere. This is not a circle, by the way. This is a cut from the circle. So this is a cross section from it. So this radius now is C, and the outer one is D. So this radius now is D. Similarly, this is the shell basically we're talking about now. I know the electric field inside is 0 too. So whether they ask about the electric field or not, inside those shells, you know it has to be 0, no matter what happened from this point on, because it's conducting. Both of them are conducting. If one of them happened to be conducting and the other one happened to be insulating, then the conducting only will have an inside of it an electric field that is 0. The insulating may or may not. It depends on how you work out their problem, okay? So it depends on the charge enclosed. So that is really how you're going to tackle this problem. Does this make sense, the setup at least, and the two key things that we conclude from the statement so far? Yes? Yes or no?
Yeah.
Imagine with me that this problem is worth several points. And at some point, they are going to ask you, thank you very much, by the way. They're going to ask you the electric field in those regions without really doing any kind of integration or any kind of reasoning or anything like that, other than just by looking at the statement. You already have gathered points in here. You already know the answer to this. As long as you're sure it's a conducting spheres, then you know the answer. It has to be 0, the electric field in those two regions. Okay? So let's continue reading the problem. The inner shell has a total charge of plus 2q. Okay, so they take a charge of plus 2q and they put it in the inner shell. So there is a 2q charge in here. I know for a fact that q inside is equal to 0. There is no charge in here. So this charge better be on the inner surface of radius A, or the outer surface of radius B, or a combination of both of them. Meaning I could have one q inside and another q outside, or half a q inside and 1.5 q outside, or I could have 1.5 q inside and half a q outside, or I can end up with a negative 5 q's if you like inside and 7 q's outside, so that the total is still 2 q's. No matter what, this is a conductor. It cannot have charges inside, because if it has charges inside, they will create their own electric field and they will move the other charges around, and they cannot stay there. So because of the free communal basically behavior of these charges, until they reach the edge, at that point they cannot borrow from anywhere else. So they will be stuck to the edge, to the surface. So this is what the 2q means now, because it's being conducting. So this 2q cannot exist inside the bulk of the conductor, but it can exist actually on the edge, on the surface. And we have two surfaces now for this shell, an inner surface and outer surface. How much is in the inner surface? I don't know at this point. How much is in the outer surface? I don't know at this point. But I know they add up to exactly 2q, algebraically. Okay? So that is basically what is given for us. Now they say also, and the outer shell has a positive 4q. So again, we added 4q in here. We know the same story. There is no charge enclosed in here. So the q enclosed is 0. So all the charge in here can be on the outer, on the inner surface or the outer surface. Nothing can exist in the bulk of this conductor. So if you have 4q, you might have 2q on one side and 2q on the other side, or 1q on this side and 3q on the other side, or 0q on one side and 4q on the other side, or negative 1q on the one side and positive 5q on the other side, or negative 2q on one side and positive 6q on the other side, or negative 10q's on one side and positive 14q's on the other side. Which side I'm talking about, it doesn't matter. At the end, they will add up to algebraically 4q's. Make sense? Yes or no?
Speaking for myself, yes.
Okay, thank you very much. Thank you very much. I really need you guys to be interactive with me, okay? Because I want to make sure. I mean, if we were in class, believe it or not, I would really not move until at least I see that you guys are with me, okay, following. Because especially now being online, I know I am the only one who has his video right now on, and that's cannot really tell exactly what you guys are up to, how you feel about these things. Okay. Question A. We're getting into the meat part of it now. Question A. Okay. Calculate the electric field E, magnitude and direction in terms of Q, and the distance R from the common center of the two shells. Okay, the direction first. No matter where we calculate it, it's going to be radial. The reason why is because both of the shells, they tell you specifically they have spherical symmetries. So if you're not sure, just basically close your eyes. I'm going to spin this, if you argue that it's not actually radial, I'm going to rotate the spheres in such a way that the direction you chose now is altered. So you ask you, did the spheres change in terms of their charges or their symmetry? You say no. Then it tell you, how come then the electric field that you chose has changed? You say, oh, then I must have been wrong. The only way to retain the symmetry in this case, if E is radial. Okay, so we know the direction that E, at least in terms of the direction, is in R hat, radial. Okay, it cannot have a lateral component one way or the other. Okay, that answers that direction. Now the magnitude. The magnitude, they said to calculate it, I for R less than A. Inside everything in here, inside. So what I'm going to do in this case is I'm going to do the following. I'm going to take a Gaussian surface. And inside the Gaussian surface, I will argue that the electric field is uniform in there. That means it's constant in magnitude throughout the entire surface because of the spherical symmetry, and it's radial. I just argued that. So the flux of the electric field must be equal to E times the area, and the area of a sphere is 4 pi r squared, is equal to the charge enclosed divided by epsilon naught. How much charge do I have enclosed in this green surface? How much charge do we have inside that green surface?
Is that 0?
We don't have any charge. Very good. Thank you. So that immediately makes the electric field equal to 0. So here E is 0 too. Good. This is simple. We did not really do much calculations or much integrations whatsoever. All we did was use Gauss's law. So
Is that equation the flux equation EA equals Q over epsilon naught? Is that
yes,
considered
the
flux
Q
equation?
enclosed. This is the
Okay.
Q enclosed.
Okay.
That is the key. And since I'm looking at this green surface, I have nothing enclosed in it. That's why I put 0. We put 0 in here. Okay. Correct?
Yeah.
Okay, let's move on to the two I's now, or two of them. This question. Apparently, we're going to go through everything in here. I, or 2, okay? When R is more than A, but less than B, guess what? We already did that. We are here inside the conductor now. E is 0 because It is a conductor. We don't need to do any Gauss's law or anything like that. We know it's a conductor, so there is no electric field inside the conductor. Because if there is an electric field inside the conductor, the free charges start to move around. And when they move around, they will cancel that electric field. So some of them will move to the left, some of them will move to the right, and at the end, there will be no electric field. End of the story. Okay? So that's the reason why we don't have any electric field inside the conductor. So that's easy, isn't it? So we get a bonus points in here for doing nothing, basically, just remembering how conductors work. So let's go to triple I. Is this clear to you guys so far?
Makes sense to me.
Okay, thank you, Justin. So let's look at the triple I's now. Triple I, it says when R is more than B, actually, but less than C. That means we are in this space now. We are between the two shells. So I'm going to choose another Gaussian surface now. So we are here. On one side, the electric field must be radial and must be the same throughout the entire red sphere because of the spherical symmetry. Again, if you argue it has one value in one location versus the others, all I have to do is just spin my entire geometry. And I ask you, did the distribution of charge change? Because of spherical symmetry, you should not say that it changed. It did not change. So how come now the electric field changed in magnitude? Then the only answer to that is the magnitude of the electric field is the same throughout that sphere because of spherical symmetry. Therefore, I'm going to say that the flux of the electric field on this side is equal to the area. The electric field times the area. And the area is 4 pi r squared of that of a sphere because of spherical symmetry. So this is a multiply, not equal, okay? So this is the, can I erase this thing in here? Okay. Okay, cannot, let me use the lasso tool, maybe I can get rid of it. Delete. And this is not a minus, okay? Man. Okay, so this is a multiply. Okay, this is the electric field that was inside the integral, but because it's constant in magnitude, I took it out. It has the same direction as the area. So the dot product became just the product of the magnitudes. And then the area itself now in this case is just 4 pi r squared. Okay. This is equal to the charge enclosed divided by epsilon naught. How much is charge enclosed inside the red sphere? Can you look at how much charge do we have enclosed inside the red sphere? Do we have any charge at all enclosed in the red sphere?
No.
Look at the inside, complete inside the red sphere. Do we have a charge at all? By the way, the inner shell. There. Yeah, do you see the 2q? That is actually what I was going to say. There is a 2q coming from that inner shell. It's included in that red sphere. Do you see it, Matthew?
Yeah.
Okay, so yeah, there is a 2q. So don't forget about that 2q. So we have a 2q now. Make sense? Because remember, we have a charge of 2q on this shell somewhere, whether on this inner sphere or the outer sphere, or a combination of both of them. So we definitely have a 2q inside the red sphere. And it's coming from the shell. Make sense now?
Yeah.
Okay, so that means that the electric field, cancel this quantity and cancel that quantity. That means the electric field in this case, E, is equal to Q over 2 pi epsilon naught divided by the distance squared. So this is how much electric field is inside that gap between the two shells, the inner shell and the outer shell. Okay? So we answered question I, or 3, okay? Part 3 of question A, okay? IV, the fourth one. When R is more than C but less than D. Do we even have to do this? Do we know the answer to that? When R is more than C but less than D. We are inside the second shell now, the second conducting shell. We know the electric field in there is. So now R is more than C but less than D. E is equal to here inside this conducting shell. How much is the electric field?
Well, it says 0 right there.
It's a big fat 0. Thank you very much. Have a nice day. Because of the same reason. Because it's a conductor also. We don't have to do any Gaussian surface or anything like that. We know it's 0. Make sense? Yes?
Again, makes sense to me.
Okay, very good. Thank you, Justin. Okay. And probably the last one is, and that is 5. 5 is for R greater than D, way outside. Okay, now we have to do some Gaussian surface, okay? So which color we didn't use? We used green, so let's use this color in here. So now we are here. So this is the surface. We are at a distance away from the center, distance R more than D. This is D, by the way, the outer surface in here. I'm going to take again by symmetry, the electric field must be radial everywhere in this sphere, okay? And if I take a patch of surface in here, the surface itself is radial, so the dot product dA times E is equal to E times dA without the vectors because both of them are parallel to one another. Cosine of 0 is just 1. And then the electric field must be the same in magnitude. So if you tell me this is 10 Newton per Coulomb, this also must be 10 Newton per Coulomb. This everywhere is 10 Newton per Coulomb. Because if you argue saying, oh, this region actually, I think the electric field is 5, okay, Newton per Coulomb. And this is, it's fine, it's 10 Newton per Coulomb. Tell you close your eyes. Watch this point. Yeah, you said this point is 5. Watch your eyes, close your eyes. I spin my geometry. And then if I do it, this point in here that was 5, if the point that was 10 will move and replace that one. And now this becomes 10 Newton per Coulomb. I ask you, did anything change for the charge distribution? You say no. It retains, it should be the same because of the spherical symmetry. So how come the value changed from 5 Newton per Coulomb to a 10 Newton per Coulomb? Oh, you must have been wrong then, because then it can not be different than anywhere else. By spherical symmetry, the electric field must be the same. So again, on one side, I have E times 4 pi R squared, because E comes out of the integral because it's the same throughout the surface. So just the surface times E must be equal to the charge enclosed divided by epsilon naught. Now look at this gray surface. This is a surface, by the way. How much charge is enclosed now?
Wouldn't that just be all the charges inside added together?
Absolutely. Count everything that is enclosed. And that would be?
Was that 6Q?
6Q. Do you guys agree with Justin? So this is 6Q. Okay? Everything. Count everything. Don't forget anything. That is basically it. So again, this result now, if I do the algebra now, it's just a matter of, so simplify, so I'll be left with a 3 in here, Q, divided by 2 pi epsilon naught times the distance squared, okay? Make sense? Make sense, everybody? Are we good?
Yeah.
Okay. Okay, so we have the electric field now, everything. Look how what that statement made it for us. Okay, we already get 2 out of 5 correct just by looking at the statement of a problem. All we have to do is just look at it, and then we get some, even if we don't know how to do the rest, or we get things wrong in the algebra or things like that, this we cannot miss. This one also is easy. So 3 out of 5 is already done for us. The only work that we really had to do was here for part 3 and part 4, and even then, it's kind of easy because of the fact that we know how much charge is enclosed. So the algebra and the symmetry in there and everything. So that's basically what we have in here. Okay, so this part is done. Hopefully this part is useful for you guys. Now, graph the radial component of E as a function of R, function of distance. So we need to graph this thing, okay? Here is the electric field E, the components. So we're not looking for directions. And here is R. Here is a point A, that's the inner surface. Here is a point B, that is the second, the outer surface of the inner shell. This is C, the inner surface of the outer shell. And this is D, the outer surface of the inner shell, the outer shell. So basically the electric field, if you notice, was 0 inside because there was no charge enclosed. Let me draw it with a different pen, probably with a thick pen also. That's for good measure. So the electric field was 0 inside because there was no charge enclosed. So the electric field is 0. The electric field inside up to B is 0 because this is actually conducting sphere. Then when R is equal to between B and C, it's this number. So initially I plug in R equals to B. So its value initially is equal to this value, which is Q over 2 pi epsilon naught times 1 over B squared. Okay. And then it drops in this entire region like 1 over the distance squared. Up when we reach C, we're going to have this much value, and it drops. So this value now is Q over 2 pi. I am using a thick pen. I should not really use it for this writing in here. C squared. So this drops like this. So it's discontinuous in this point. Jumps, if you wish. Okay. Then inside the second conductor between C and D, we found it to be 0. Between C and D is 0. So it's discontinuous in there. And then it draws like 3Q over 2 pi epsilon naught divided by a distance squared, depending on how the Q and the C and the D are related. So it could come up from this point in here. That has coordinates 3Q divided by 2 pi epsilon naught times 1 over D squared, and drops toward like this. So it goes to 0 when R goes to infinity. So this is the function that we're supposed to plot. Make sense? The graphing. So it's a good idea to do it on calculator, but you have to do it as a function of Q over 2 pi epsilon naught, okay? And you have to have some nominal values in here to be able to graph it. Otherwise, you need some numbers, okay? Does this graph make sense to you guys? 0 because there is no charge, 0 because it's conducting, and now it drops like 1 over distance squared between the two shells, and then it's 0 inside the second conducting shell. So there is a discontinuous function in here, and then it drops like 1 over distance squared once we reach this point. Are we good so far?
Yeah, it makes sense to me.
Okay, so the graphing was easy. Thank you. Graphing was easy. Part B. So this whole thing is part A of the problem. So let's look at part B now. I know I am a little bit verbose and detailed in solving the problems. And I hope you guys, once you learn these things, you're going to be at ease with them so that you don't really need to spend that much time so that we can basically go on. But if you need me to slow down, I'm more than happy to slow down. If you think that we're going too slow, please let me know so that we pick up the speed too. Good. Again, Part B, what is the total charge on A, on 1? So we want to know the total charge on I. Where am I? The inner surface of the small shell, basically for R equals to C, A, I'm sorry, on this surface. What is the charge there? Well, for that, let's go back into the shape in here and note that the electric field, so this is, let me draw another shape because that's going to be complicated. That is getting complicated in there. So let me get into the drawing now again. So we have the inner shell only, okay, at this point. So this distance is A and this distance is B. And we know the electric field in here is 0. So this point inside is 0. It doesn't matter where. So I'm going to check, choose an arbitrary point. I'm going to apply Gauss's law there. And if I apply Gauss's law, I know the electric field is 0. And by symmetry, it has to be radial if it exists at all, and times the area. So the flux, no matter what, if I do E dA, it's going to be 0 because E is equal to 0. Inside, this is inside the conductor. Because E is 0. And this 0 then must be equal to the charge enclosed divided by epsilon naught. So what must be the charge enclosed then? What must be the charge enclosed in order to make 0 equal to the charge enclosed over epsilon naught? Come on, guys. What's the answer? What would that be? I have 0 equals to Q enclosed divided by epsilon naught. Epsilon naught cannot be 0, it's a number. So Q enclosed is equal to, don't
That
be
would
shy.
be 0, right?
Yeah,
Q
don't be
enclosed
shy.
has to be 0.
Absolutely. So Q enclosed has to be 0. There is no charge inside this area at all. There is no charge inside the conductor, so there cannot be a charge also on this surface. So the Q in here is equal to 0. So the inner surface of radius A has no charge in it. Because if it does, it will make the electric flux in here not equal to 0. It's going to be that charge divided by epsilon naught. And we know it's 0 because of the fact that there is no electric field inside in here. So if I calculate the flux throughout any surface in here inside the conductor, it has to be 0. So that's why that charge is exactly 0 on the surface A of radius A. Okay? Make sense? I'm hoping the people who are not talking, they're following, and if please are confused or you need some explanation or why is that, please let me know, okay? Because this stuff is very, very important. So I'm hoping that you guys are following. And part 2. So we answered the question. For R equals to A, the charge is equal to 0. So there is no charge in there. Part 2. For the outer surface of the small shell, that means R is equal to B. For that surface, the surface whose radius is B, surface whose radius is B. This surface, actually, we want to know the charge. We know for a fact there is a 2Q charge on this entire shell. That 2Q charge cannot exist on the inner surface. We just made the case for it. It cannot exist in the bulk of the conductor because it's a conductor. So the only place for the 2Q to exist is actually on the surface itself, surface of radius B. Does everybody follow the reasoning in here? So the Q in this case is 2Q. The charge on this surface is 2Q. Because, man, we know we have 2Q on this shell. 0 inside plus 0 on the inner surface. So we're left with 2Q on the outer surface. Do you guys understand? This is basically the reasoning based on charge conservation. Since we must have 2Q somewhere, and we cannot have it inside because it's a conductor. We cannot have it on the inner surface because we have a constraint in terms of Gauss's law for that, that region. So the only place that we have for it is the 2Q must be on the outer surface. Make sense? Yes? Come on, guys. Yes or no? Please let me know if it's kind of still iffy, okay, too. So it's not like a yes or no. If it's like in between, it's fine too. I need to know. Good? If you guys are writing, I can't really read anything right now because I'm in the sharing screen.
Yeah.
Okay, very good. Thank you. Part 3. Okay, of this problem. It says on the inner surface of the large shell, that means R is equal to C. This surface of radius is C. So let me go back and redraw this shape now. So we have an inner surface that is of radius A and that is of radius B. And then we have now an outer surface of radius starting from the same point, C. And now we still have that outer surface of radius D. Okay, so this is the second metal now. Second conductor. I call it metal because metals are conductors, okay? So we want to know the charge in here of this radius C, this surface only. So there is a sphere, an inner sphere inside, and we want to know how much charge is enclosed. Same thing like the first part, we're going to come up with the same trick and choose this Gaussian surface inside. And the electric field inside the conductor is 0 anyway. So the flux is going to be the integral of EdA. And that is going to be 0 because this is 0. So the flux is 0 here. There is no flux in this red surface, red sphere. And this must be equal to the charge enclosed divided by epsilon naught. I know already I have a positive 2 charge in here. So there is a positive 2Q in here from this surface. I need to have something in here to make the whole thing equal to 0 because I know from the inner surface I have a positive GQ. I need to add something to it to make this whole thing equal to 0 because the charge enclosed need to be 0 now because of the same reason, since the flux must be 0 because there is no electric field inside that red sphere. So what should I add to the 2Q to make it equal to 0? Or probably what should I subtract from it to make it equal to 0? Come on, guys. I need a little bit of energy in here. I mean, I know you guys know it. Just say it. Don't be
Would that
shy.
be negative 2q then?
Thank you
Or
very much.
just-
Have a nice day. Yeah, it's a minus 2q. So we need a negative 2q to compensate for this one because we need the flux on this red surface to be 0. I cannot have this negative 2q inside this part of the bulk of the conductor because it's a conductor. I cannot have it in the empty space because it's empty anyway. This one, I cannot have it in there anyway because it's already done for. It has 2q only. So the only place for the negative 2q to be is in here, in this inner surface. That's the only way for me to have to have a 0 flux for the electric field, because I know it's 0 because the electric field itself is 0. Since E is 0, its flux must be 0. Therefore, the charge on this surface must be equal to negative 2q. Okay? Make sense? I know it's sometimes hard to wrap your head around it, that how come you spread 4q and now all of a sudden you're telling me I have a negative 2q? Yes, the charge will adjust themselves. Negative 2q must move in here to cancel this 2q, otherwise there will be an electric field inside the conductor. So initially, maybe there was an electric field, but charges will migrate enough to compensate for this 2q so that there will be no electric field in here, no flux for the electric field. And then you said, okay, I put 4q, remember, on this charge? Well, how much should I put in here? That's your problem. Do you understand? As far as this part of the problem, that is, the charges need to fix that on their own, okay? We know we have a total of 4q in this guy, okay? We have a positive 4q. Negative 2q in here is inside in here. So how much should we have in here on the outer shell? Because we cannot have a 4q in the side at all. We cannot have any charge whatsoever inside the conductor. Because they are free to move, they must go to the edges. Negative 2q are in this edge, they are in this inner surface. How much should I put in here to make this whole thing 4q? How much should I put outside to make this one, this whole thing add up to again 4q? I know you know it. And that is because of the conservation of charge. I must have 4q no matter what, because I put 4q initially in there, okay? Negative 2q moved in here. So I need to have something in here so that if I add it to the negative 2q, I will end up with 4q. What should I put in the outer surface now? Come on, guys. You can say it. I know you know it. What number should I put in here?
Is it negative 4q to balance?
If I put negative, okay, I have to put an x in here in such a way that x plus negative 2 is equal to 4q, basically. What should this number mean?
So you need a 6q then?
We need a 6q, yes, absolutely. So that if I add it to the negative 2q, it's going to be 4q. Okay? So I know probably they're going to ask about the outer shell, outer surface from the outer shell. But if they do, we know by charge conservation, it has to be exactly 6q. Because if I add 6q to negative 2q, I will end up with 4q. Because charge must be conserved. So if you move negative 2 in here, and you need to remain at 4q overall, this is 6q. By the way, please don't confuse this number. There is no such a thing of a charge inside. Charge inside the bulk of the material is always 0. So the charge inside is 0. However, on the outer surface, yes, you can have charge. There is no problem with that. Okay. Is my internet behaving not good? Maybe there is a delay or something. You guys hear me well?
Yeah.
Okay. So we argued, first of all, the negative 2q based in this argument, because the flux on the red region must be 0. And it's the sum of this 2 charge, 2q's, plus something divided by epsilon naught must be 0. And that something better be negative 2q. Okay, so we know the inner surface of radius C must have negative 2q charge on it. So the part 4 is probably where we get into outer surface of the large shell. The outer surface of the large shell, okay, where r is equal to d actually, that's this surface of radius r equal to d, not the radius itself, it's actually a sphere, okay? So the charge in there must be equal to positive 6q for charge conservation, because we know we have a total of 4 q's on the entire outer shell. Minus 2q is needed inside to compensate for the other positive 2q to make the E field inside the conductor equal to 0. Now I must have a positive 6q because negative 2q is needed to do that. So I need a positive 6q to keep 4q. So we need 6q, positive 6q that is, to compensate, to add up to 4q, namely negative 2q from the inner one plus positive 6q from the outer one is going to be positive 4q. Now we have everything fully accounted for. Okay. You guys understand this problem? I know we spent a long time on it, but I'm hoping that you guys have a better appreciation now of Gauss's law and how it helps us solve these problems with conductors. Yes? It's okay if it's not clear 100%. Please let me know, okay? I mean, I know that you guys are going to practice these things more and more. I mean, I've been doing this for a long time, so probably I have an edge when it comes to this one, but it only comes with practice and basically going through these materials and understanding them. And the only way to understand them is by practicing more and more. Okay. Can we move on to the next problem, or is there anything that I need to clarify for this problem?
I don't think so. I think that was pretty good.
Okay, very good. So please go through these things again. Try to do it on your own. You have the video. Come back to it if need be. This is an added thing that hopefully you guys are taking your notes and you're doing with me, because that is the thing that I require when we do practice problems, is that you guys go through them again. And please find the mistakes that I make, because I make mistakes, okay? And let me know in the discussion, hey, this one was done not correctly, please, or why did we do it this way? Could we have done it differently? Maybe you come up with a different approach that can be better, and sometimes it does. So this is not out of, when I'm saying that, it's not like I'm saying it as a challenge, okay? So I'm really saying it so that you can come up with probably better explanation or better approach to it that might be useful. And then the other thing also is that every time we do problems like this one, or a lot of times, this one doesn't have numbers and it has Q and things like that. So when we have numbers, I rarely do the numbers, okay? So I'm counting on you guys to finish the calculations, okay? Number one. And number two, to have a feel for it. Because when you write something, you're going to be feeling better with it. You're going to feel more confident about what Gauss's law mean and what all of these things mean, okay? Good?
Sounds good.
Okay, thank you. Okay, so let's do problem 55 now from the next page. I don't know which page. It's problem 59. 9 from the other book, okay, from the 15th edition. I'm looking at it laying around on the other side. Okay, for that, we probably are going to get Excel because it gives me a big table in here. It says in one experiment, the electric field is measured for points at distance r from a uniform line of charge that has a charge per unit length lambda and length L. Well, L is much, much larger than, so let's go back into the problem in here. Oops, I need to actually share that. I'll just go by myself. So right now we're doing problem 55, okay, from the 15th edition, or 59 from the 14th edition. So in this problem, they tell you have a long rod, okay, of length L, which is much, much bigger than R, where R is this distance. I know in the lecture, I used the symbol Y for this distance, but you could use R. We know the electric field, we measure this actually in class to be epsilon, E is equal to lambda divided by 2 pi epsilon naught times the distance R. Okay, that we did in class, okay? So that is for a rod, an infinite rod. We called it an infinite rod in the case when its length is much, much bigger than how far you are, trying to find the electric field for it. That's exactly the situation they want you to be. In the second experiment, the electric field is measured for points at a distance r from the center of a uniformly charged insulating, that's a keyword, insulating sphere that has volume charge density rho and radius r. So basically they gave you the radius. So here is a sphere of radius r, where r is equal to 8 millimeter. Okay. But they measure the electric field, and it has a uniform charge distribution rho. So rho is constant, so we don't have to worry about the business of integrating and things like that. So it's kind of easy a little bit. And they tell you where rho is, where r is the greater than r. So they measured the electric field at some point in here where r is bigger than r. And we know the electric field for this one is given by q over 4 pi epsilon naught times 1 over distance squared, okay? Because r is bigger than r. That's what we found in the lecture, actually. It's chapter 22, okay? Using Gauss's law. And here, I forgot to mention that this is actually radial. The electric field is pointing in this direction. So this is E as a vector. And in here, it's pointing away from the rod. Okay, so if you're curious about its direction, that's its direction. Okay, so both cases, it's in the same direction as R, the vector R. Okay. Now, the result of the two measurements are listed in the table, but you are not told which set of the data applies to which experiment. So somebody hands you, okay, I've got a bunch of data, here it is, okay, for doing these two experiments. And then he left or she left and left you on your own. Now you have no clue because they have the data separated in two basically columns, 3 columns actually. One of them is for the distance and the other 2 for the two measurements for the electric field. And you have no clue which one is the sphere and which one is basically the rod. For each set of data, draw 2 graphs. One for ER squared versus R, and the other for E times R versus R. So we're going to take this one, and we're going to multiply it by R squared. So if I multiply it by R squared, the R squared cancel the R, and this should be simply equal to 2 pi over epsilon naught times R. So this is going to be a line like this, okay? So this is graph 1. Graph 2, to multiply this by R and draw it. So the R will cancel the R, and we're going to end up with lambda over 2 pi epsilon naught, okay? So this should be a line. So if I see it's a line, I know exactly that this is a rod. If I multiply it by R, okay? And I see it as a line, I mean, I see it as a horizontal line for this one, or I see it as a line growing up. So I know that this is the rod, actually. The same thing, they said to do the same 2 graphs for the sphere. If I take this one and multiply it by R squared, so it's going to be E times R squared is going to be Q over 4 pi epsilon naught. So this is going to be a constant. So the graph in here, they multiply by, so this is the by r squared, and this is by r, okay? The graph by r squared is going to be a line in this case. So this is by r squared, okay? So it's the opposite of the other graph that I know. This is actually a sphere. If I multiply by r, where one of the r's cancel the r squared, and the function should be q over 4 pi epsilon naught times 1 over distance. So this should drop exponentially like this one. So it's going to drop, not exponentially, I'm sorry, like 1 over power law, 1 over x basically. So I know if I see this is multiplying by r. So if I see this behavior, I know I'm dealing with a sphere. Okay. So that is basically how I'm going to analyze this thing in here. So we're going to take the data, put it in Excel, and draw these two graphs and see which one is actually the sphere and which one is the rod. So I'm going to open Excel in here and share with you Excel. So let me stop sharing this OneNote and share with you Excel. Where is Excel? Oh, here it is. Okay. So in this Excel spreadsheet, do you guys see the Excel spreadsheet? Yes or no?
Yeah.
Okay. So I'm going to take the data. The data for R is in centimeter. Okay. It's very important to remember the units when you're dealing with Excel. Okay. Because you might need to make conversions while you're there. Okay. So it's 1 centimeter, 1.5 centimeter, 2 centimeters, 2.5 centimeters. If you're not familiar with Excel, this is a good time to practice it. Okay. Because you're going to be needing it when you become engineers or scientists or something like that, okay? This is one of the best tools that you're going to be saving a lot of time doing stuff with it. Otherwise, you're going to do it by hand, and you're going to be make a lot of mistakes. 3.5, by the way, when I give you exams, there will be problems like this one where you need to know how to use Excel to get things done. Short of doing that, you're going to waste a lot of time doing it by hand. And then 4, okay? So this is R. Now, measurements for the electric field. So the electric field for measurement A. So I'm going to call it the electric field for measurement A. And this is in the units of 10 to the power 5, basically Newton per Coulomb. So I'm not going to write Newton per Coulomb. I know it's a Newton per Coulomb. So please, if you don't, I mean, it's much better to write it actually, okay? Especially since it's in SI, I don't worry about it. This one I worry about it since it's not in SI, it's not in meters basically. So I might need to do a conversion at some point. So this one is dropping as I expected. Both of them are dropping. One of them drops one over distance. The other one drops like 1 over distance squared. At this point, I don't know which one is 1 over distance squared or which one is 1 over distance. But it drops from 2.72 to 0.79, 1.34, 1.07, and then down to 0.902, 0.770. There are 3 sig figs in here, by the way. Excel doesn't care about that. 0.677. Excel will just basically round it. I mean, basically get rid of the extra zeros. Doesn't care about sig figs. Okay, for the measurements for the electric field for part B. Again, it's 10 to the power 5. This is just notation, by the way, only. It's not a formula or anything like that. But at this point, it's data. Again, it's dropping 5.45, 2.42, 1.34. Wow, this number repeats. It's the same number in here too, man. Okay. Don't read much to it, okay, for data, okay? So sometimes this happens. 0.605 and 0.443. There are also 3 sig figs in all of these measurements for the electric field. Okay. Since they ask us to graph this times r squared and this times r, I'm going to write in here EA R, okay? This is not a formula, just basically r squared, okay? It's just basically a writing for my own notation so that I know exactly what I'm plotting in here, okay? And this is EA R to the power 4. No power. Okay, ER, I'm sorry, ER. Okay, again, Excel has this weird thing in here that reformats things for you, which is kind of bad. Let me see if I can control that. If you do an apostrophe, I think you can retain the format that you have in there. Okay, just for your own convenience, because that's how I want things to look like when I'm graphing things. Okay, so I'm going to take this cell and multiply it by this cell, keeping in mind that the units in this case are in Newton per Coulomb times centimeter. All I care about is just the behavior. I really don't care about the number yet, okay? So again, this is equal to the same cell times this number now squared to the power 2. Now this is math now. I'm going to take these two cells and copy them, Control C, that's what I'm doing. I'm going all the way down and Control V basically to paste the formula. So this did the same math in here for me. If you look at it, that's exactly what these numbers are. And this is basically what the other one is. If you don't like Excel and you would want to do it manually, that's up to you. You can do that too, okay? But make sure you don't make mistakes. I'm going to move a little bit further away. I'm going to write the same thing, EBR squared, just to keep the symmetry going. Man, I don't like this. It doesn't matter. So you have to write it again to really tell it that I want it. So EBR, it's going to mess it up, okay? Okay, good. It retains it. Okay. So again, oh man, I flipped the order. This should be squared. See, I'm glad that you guys are in here. And this should be just to the power 1. I flipped them. Okay. Now I have to redo this calculation in here. Paste the correct numbers. So basically, I have them backwards. So this is EAR squared, and this is EAR, the experiment, the electric field. Don't forget, I have 10 to the power 5 and divided by 100, okay? If I really want to, the correct conversion. In here, actually divided by 10,000, because 10 to the negative 6, 10 to the negative squared is 10,000. I mean, 1 over 10,000. So you know what I'm saying in here. So make sure the correction, if you really care about that, you could have done it in here, okay? So it's going to be times 10 at the end of the day. Anyway, so the same thing in here. So it's going to be EB times the radius squared now, this one squared. Okay, and this one is going to be simply this one times just the radius. So I'm using the star for the radius, for the multiplication, and pasting the other formula, and that's it. So now if I copy these two formulas and move them all the way down, I know now, oops, what happened? Control Z. Did I mess up the formula? A3. Okay, yeah. So this is working. A4, A5. Yeah, so this is correct, okay? Because the last thing I would want to see is A8. Yeah. So the last thing in here is we'll see something wrong with the formula. Okay, we're gonna plot this as a function of R. That's what they want us to do. And this as a function of R. So I'm gonna select the x-axis first. I'm gonna put my finger on the control key and select the other two cells in the same time, okay? So if you're not familiar with Excel, this is a good time to practice it too. I'm going to come to the insert in here. I'm going to choose this plot, okay? And look at this thing in here. It's telling me experiment A, if I multiply it by R squared, I get this line. And if I multiply it by R, I get this line, exactly how I was expecting for the behavior of the rod need to be. So this data in here is for the rod. Okay, makes sense? So the other one must be for the sphere. Let's see if how we expected it is going to work or not. So let's do the same thing. I'm going to select now with basically the mouse, put my finger on the control key, and then I'm using Windows, by the way. So if you're using Mac, you're probably going to use Alt or something like that. I'm not. You're going to, no, the control, I think probably is the same thing. Anyway, I'm going to come to the insert again. I'm going to choose the charts. I'm going to choose this one in here. And look at this, exactly, almost exactly like I expected it to be, okay? If I multiply it by r squared, it's the blue line. It should be about constant. If I multiply it simply by r, because I have in the denominator r squared, it should drop like 1 over x, basically. Let's just, for the sake of this, to see exactly what's going on in here. Where is my... Here is how we... I'm sorry. Oops. Here is how we expected it for the rod. It's going to be constant when I multiply it by r. When I multiply it by r squared, it's going to grow linearly. When I multiply it by r, the number that I get, that constant number, would be exactly lambda over 2 pi epsilon naught. When I multiply this one by r squared, it's going to be q over 4 pi epsilon naught. So what I'm going to do in here, I'm going to come back to Excel. So let me stop sharing again and go back to share the Excel file. So once I multiply this one by r, I got a number that is more or less constant. It's the red one, okay? This is E by R, it's this one. So I need to find that average. So that is actually lambda over 2 pi epsilon naught, okay? So that is equal to average, the word average itself, open parentheses, and I'm gonna choose this numbers in here and hit enter. So the average is 2.69. Remember, has 3 sig figs. Excel gives me millions numbers, okay? But in this case, because I'm assuming this is an exact number, that's what they did. They moved every half a centimeter away. So they were very accurate in here in their measurements. But the confusion was actually in terms of sig figs was about this number, okay? It has 3 sig figs. So I'm going to retain 2 sig figs in here. So the answer is 2.70. Because if I round up in here, it's going to make it 0 and then all the way to, so it's 2.70, okay? And that is lambda where is my, what happened to my OneNote? Did I delete it? Where? So, and that is, if I multiply by a constant, that is actually this one. That is this number. The only trouble with is the units. I have to be very careful with the units. When I multiplied by r, r was actually a centimeter. So this number was 2.7 times 10 to the power 5 times r in centimeters. So I have to multiply by 10 to the negative 3. Okay. So this number is lambda over 2 epsilon naught. So now I can find what lambda is from this one in here. I know what 1 over 4 pi epsilon naught. So all I have to do is just move things around and I'm in business. Okay. Negative 2, not negative 3. I'm sorry. Centimeter is negative 10 to the negative 2 centimeters. Okay. So technically, we should be able to find lambda. Did I make a mistake in here in the conversion? 2,700 Newton per times centimeter. Yeah, that's correct. Okay. So, oh, I'm sorry. Those numbers are multiplied by 10 to the power 5. So they amplified them. So actually, there is a 10 to the negative 5. I'm sorry about that. So actually, you have to multiply by 10 to the negative 5. Okay. I really have to check on this thing here because it seems like I'm going to get a huge number in here if I don't do that. So I need to think about this one. Please plug in the numbers and see if lambda will make sense to you. How many coulombs per meter? Okay. You might end up with a big number because of the fact that this is a meter. It's not the entire charge. So you might have less or more depending on how much charge you have in here. Okay. So this is 1. Let's look at the other one in there. Let me stop sharing the screen. Let me share with you the Excel file. In the Excel file, again, it's the blue now. Multiplying by r squared is the one that is going to be the constants. And this number doesn't change, okay? This number clearly changes from 5 all the way to 1. And this is this one, okay? The other one in here, I didn't compare with it. When we multiplied by r squared, also it grew from 2 all the way to 10. So that could not have been constant. This is the constant, and this is where your constant is in the second one. So for the second one, we're going to come again in here and do the same thing, equal to average of these numbers. Again, it looks like it's not a straight line as much as the first one was. This one is actually a straight line. This looks like it's a kind of jaggedy a little bit, which means that this approximation has a little bit more errors than the first one, okay? And you can find the error, actually. You can go and do a fit in this case and see exactly trend line. And linear, let's more options in here. What happened? And we want to display the equation, and we want to display the r squared. So this is fitting with this much with a line. So actually, I don't want a linear. I want a constant. Do I have anything that says constant in here? Or custom? A, can we do it? I don't know. I've never done this. Nope. Anyway, because it's trying to fit it with a not this term in here, polynomial, yeah, of order 0. Cannot do it less than order 2. Oh man, Excel has some limitations in here when it comes to fitting. Okay, don't do the fitting at least for this constant function. Okay, it doesn't work. So let me remove the trend line in here. So we can find the average. Here is the average. And the average in this case should be Q over 4 pi epsilon naught. So this number should be exactly Q over 4 pi epsilon naught. From here, you should be able to find Q. Once you find Q, let me stop this one. And share with you this one. So when we multiply by r squared, this should be a constant. So, and this constant actually. So this is the constant that we should have found. Q over 4 pi epsilon naught is equal to that constant that is coming from the average from Excel. From here, we should be able to find that charge. Q is going to be 4 pi epsilon naught times that constant. Remember? Oh, I think I know what went wrong in that analysis. Okay. Remember, no, I think we were right in the beginning with it because I was worried about this number being too big. Remember when I divide by 4 pi epsilon naught is 9 to the power 9. As a matter of fact, this answer for lambda looks a lot better now since I'm at better now. So it's going to be 10 to the power 3 times 9 times, sorry, divided by 9 times 10 to the power 9 times 2, actually, because I know if I plug in the correct answer for epsilon naught, this is how it should go. So this is correct, 10 to the power 5 and 10 to the negative 5. So it's going to be 10 to the negative 4. So we're in good shape. And it's going to be in Coulomb. So that was correct, the initial number that I have in there. So it's a positive. Same thing with this one. It's going to be a positive. So whatever we find from that experiment, which was, I'm going to glance back quickly at Excel, 5.41. The constant was 5.41. Times 10 to the power 5 times the centimeter squared. Centimeter squared is 10 to the negative 4 meters squared, okay? So now this is going to be the charge. So the charge is going to be exactly equal to 5.41 times 10, which is 54.1, divided by 9 times 10 to the power 9. The reason why I have to divide is 4 pi epsilon naught is exactly 1 over 4 pi epsilon naught is equal to 9 times 10 to the power 9, roughly, okay? It's 8.99 times 10 to the power 9 SI, okay? So if I plug in the numbers, this is correct now. So this is 54 divided by 9, which is roughly 5 times 10 to the 9, or roughly about 5 nanocoulombs, which is good because I don't want to find the big charge. So charge Q is 5 nanocoulombs, but they don't ask us for that. They ask us for rho, the charge distribution rho. That is because it's uniform. It's the entire charge, Q, divided by the volume, 4 over 3 pi r cubed. We know this number is 5 nanocoulombs, divided by 4 over 3 pi times the radius, which is 8 millimeter cubed. 8 times 10 to the negative 3 cubed. Okay? 10 to the negative 3 and 10 to the negative 3 and 10 to the negative 3. So it's going to be a big number in there. So when you plug it up, it's going to be 10 to the positive 9. Cancel this one. So at the end, basically, this is numerically as if 5 over 4 pi over 3 times 8 cubed. Okay? Please verify my numbers. That's your task. Go through the same exercise as I did. The purpose of this also is for you guys to be able to handle data, okay? And use Excel at it, okay? This is not a commercial for Excel. There are other products in there. So if you feel more comfortable using another, like OpenCalc, for example, which is a very, very good software similar to Excel, except it's free. You don't have to pay for it. Excel is actually free also for you as the students in this college. So you can have Excel and work with it. So there is no really reason for not being familiar with it and using it. And hopefully you will master it enough to do all of these problems. And down the road, as I said, you will have problems in the exam that are of this type. Now, granted that on the first exam, we're going to be on campus, so we don't have access to Excel. So we're going to have stuff that is a little bit hack. You can handle it with a calculator. So you don't need intensive use of Excel to get things. But the second exam, since it's going to be on Canvas, so that is what I expect you guys to do heavy stuff with Excel too. And this is actually stuff that you'll be doing in the lab anyway. Any questions about these two problems? I know I went very, very much in detail about them. And sometimes, like I said, I tend to be too verbose for you guys and too much detail in it. So if you guys think it's too much detail and that's probably not needed, please let me know. We can pick up the pace. There is no problem with it. If you think that it is too fast, actually, at some points, please ask me to slow down, because sometimes I think things are obvious, but it may not be as clear, especially if you are not used to it in the past, so that we go through it again and make sure that it syncs, okay? The only way for this one to sync, actually, and you guys will be at ease with it, is you actually do it yourself. This is not, physics is not a spectator sport. I can watch tennis all the time if I can, but I will never be able to play tennis. As a matter of fact, I don't play any other sport. The only sport I play is soccer, because I play it actually, and I know how to play it. And I hope you guys do the same thing, at least for physics. You guys do these problems and do the homework problems and do the extra stuff in there. And if for some reason you're stuck at some point, please don't waste too much time on it. Send me a message, okay? Tell me that, hey, I'm thinking about this problem and I'm reached this point in here and I have this reasoning. Do you think this is the best approach to this problem? We think through it together and hopefully we can find a way moving forward with that problem. Good?
Yeah.
Okay.
By the way, did you record the lecture or the lab part on the 25th? I know we didn't do a lab, but we answered some questions.
I did, yes, and I posted it actually. Let me check the, it should be posted. No, this is not.
I couldn't find it, so I'm not sure where you put it.
Okay. Okay. That's not this one. You're right, I don't see it. I think I posted it in another class, but not yours. That's bad. Okay, I'm going to chapter 22. Okay. Where do you guys want me to post it? Because I don't see it. You're right. You're absolutely right. Actually, it's on my YouTube account channel, so I'm going to just give you the link to it. If you want it now, I can go to the YouTube channel and find problem physics 4B. I believe that's the one. No, hold on. Where we did the problems from the homework, isn't it?
Yes.
Okay, I'm going to give you the link right now, but please remind me. I posted the link actually on the chat now for those of you who are here, but please remind me again if you don't see it somewhere in there. I'm going to send a message to everybody that we forgot to paste the link. Okay, that should be it. Okay, I know it's about 2 hours, that 1 hour and 58 minutes and 26 seconds, the recording itself. I know sometimes we start before and we can do stuff after and things like that, but the actual recording is almost 2 hours. You see that?
Yeah, was this the electric charge and electric field one?
Now this has to do with all of the homework problems from chapter 21.
Okay.
Okay?
Yeah.
All of them.
Also, if we have any other questions regarding homework, I assume we would see you in office hours.
Please send me a message all the time.
Okay.
I'm kind of tied up during the weekdays because of the fact that I have a heavy load.
Mm-hmm.
If you can find during, let's say, Monday through Thursday, that would be great, okay? If the question is only related to you, we will not record it. If a question we decide that it benefits everybody, then it's a good idea to record it and share it again so that everybody benefits from that discussion, because chances are, if one of you guys has an issue, probably some few other people also, if not a lot of people, have the same issue, okay? So it's a good idea that we post that to everybody's benefit. Now, if that doesn't work, and the chances are it's not going to be very hard to work, we will shoot for Friday, Saturday, and Sunday. The only thing I request in here is give me at least a heads up, okay? And be open and flexible to allow for whatever schedule that we come up with. Tomorrow, for example, I know I'm in a meeting from the morning all the way to 1 o'clock. So tomorrow is not going to be possible. This is a college thing, okay? That everybody is basically, at least some people who are in the committee that I'm involved will have to be in. But after that, allow me for about an hour or something to get something to eat, but then we can meet tomorrow, okay? If there's something that you think that we need to be. If you call me, if you send me a message on Saturday morning, usually I'm tied up with the soccer, but message me, then we can meet in the afternoon, or we can meet in the evening, or Sunday. I am open for most of the day, except in the evening, I have a little bit of time for myself, but that's basically it. So more than happy to work with you during weekends, whatever times that is convenient to you guys. Again, if it's a personal thing, let's say, for example, you have some minor issues that are of relevant to you, then we will not record it. Before I record, I will ask your permission, stating exactly the purpose, that this is probably useful for everybody else. Let's record this one to the benefit of everybody. And of course, hopefully you agree to it, and then we will do that and post it to everybody else.
Okay. So is the best time to reach you is Monday through Thursday, is what you said?
Monday through Thursday is hardest, actually, because I'm teaching.
Okay.
Almost basically around the clock.
Okay.
Those days. I have a heavy load. I have 3 calc classes and 3 calc classes with their labs, of course, and also 2 non-calc classes. And I like to basically, when I'm teaching, you notice that. I don't know what you guys do with the other classes, but all of my classes are held live. So, and that's not true only for your class, for all of the classes. So that's basically how I do things in here.
All right.
Okay.
Yeah.
But reach out, okay? Let's work out a schedule and we will meet for sure. Okay?
Yep.
Okay. Let me stop the recording and I will see you guys Tuesday. Okay?
All right.
Take care, Professor.
See you.
Yeah, thank you. Thank you very much.
Okay, no problem. Thank you.